All right, thank you very much. The conference organizers were very wise when they scheduled the theory talk before the observations talk, because in fact, tidal disruption events are a phenomena that were first proposed by theorists in the late 1970s to be an inevitable consequence of supermassive black holes lurking in the nuclei of galaxies. And so in this case, the theory came first. And we're just trying to catch up with observations. And I think today I can give you, and I'm trying to give you a nice overview of the observations, and I think we have some very clear examples of true candidates of this very exciting and interesting phenomenon. And in fact, the background of my cover slide here shows an example of how we discover some of these candidate events using optical difference imaging surveys. So the outline of my talk will be how we got here, what is the status of observational candidates for tidal disruption events. Most of my talk is going to be surprises along the way. In fact, most of our observations differ quite significantly from the most basic theoretical predictions for how these events should look and where we go from here. And I think there's an exciting future in this area. So this shows you the average rate of discovery of tidal disruption event candidates in the past, over the past 2 decades. And I've also indicated, so this is a cumulative number of candidates, and I've indicated the various surveys that came online that contributed more events to the current census. We now have about 24 strong candidates for tidal disruption events with an average rate of discovery of about 2 per year. And as you can see in this slide, while we've had this steady discovery rate, in just the next few years, we might have a huge jump in the number of candidates with the next generation of surveys, starting with ZTF as early as next summer, and then followed by LSST at the beginning of the next decade. So we may be dealing with hundreds or thousands of tidal disruption event observations. So this has truly been a multi-wavelength search, and I've highlighted here the different wide field surveys that have been used to look for candidates, and they've spanned the entire electromagnetic spectrum, although not yet in the radio, but from gamma rays through X-rays, UV, and an optical. And so what I'm plotting here are the candidates, the year of their reported discovery as a function here, as well as their peak luminosity. And you can see they're all hovering around close to what you'd expect for the Eddington luminosity of about a 10 to the 6 solar mass black hole. But there are some notable exceptions, which I'll talk about in a second. And you can also see there's this trend. You see this cluster of green points here. So originally, the first candidates emerged in wide field soft X-ray surveys, in particular ROSAT. But most recently, we've been seeing more and more candidates emerging from optical surveys. This is not necessarily because the optical waveband is the best place to look for tidal disruption events, but it happens to be where we have the most survey power at the moment. So I wanted to go over some of the observational milestones in this area. So of course, the first candidates were discovered in searches through the ROSAT All-Sky Survey, which is a soft X-ray survey that surveyed hundreds of thousands of galaxies. And they found soft X-ray outbursts from the nuclei of galaxies that had previously shown no indication of AGN activity. And these were very exciting potential candidates for tidal disruption events, but there was not much information about the shapes of the light curves or other broadband properties. After the initial X-ray searches, I initiated a search using GALEX in the ultraviolet, and we found 3 candidates for tidal disruption events, and these were the first time where we were getting UV light curves, and we also had simultaneous optical data in a couple cases from supernova survey data, which also caught these events nicely in the optical. And so now we had light curves with a cadence of days instead of a cadence of years, as had been in the case of the X-ray candidates. Another very important milestone was the discovery of relativistic events. So as you can see, these events here discovered by the Swift telescope really stand out in their luminosities, indicating that these are non-thermal jetted emission. And Ashley Zoderer is going to talk more about this entire new class of tidal disruption events, in which we think we're not looking at the accretion of the tidal debris onto the black hole, but we're actually looking straight down into a jet that was launched as a result of the tidal disruption of a star. With pan-stars, we detected PS110JH, which was the first time where we got a really nice sampling of the light curve of a tidal disruption event, in particular during the rise of the event, which, as James discussed, is very critical for trying to constrain the black hole mass doing the disrupting in these events. And we also caught transient broad emission lines that were clearly being powered by the event and were telling us something about the tidal debris in the tidal disruption event. Finally, the Assassin survey has most recently discovered 3 new tidal disruption events, and they're very notable because they're being discovered at very nearby galaxies, and so that's enabled very detailed multi-wavelength follow-up, both multi-epoch spectroscopy, as well as the first bona fide detections of an X-ray and radio counterpart to the optical light curves. So this has been a very exciting time, especially recently for the detection of candidates, and you could say, in general, they have some properties that are in line with theoretical expectations. I don't think James showed this, but this is sort of your general plot of what the fallback rate is of the tidal debris in a tidal disruption event. And it's actually very well determined dynamically. It's simply determined by the Keplerian orbits of the stellar debris. And you see there are 2 characteristic attributes of this fallback rate. One is that the rise time of the fallback rate is very sensitive to the black hole mass. It depends on the black hole mass to the 1/2 power. So as you go to larger black hole masses, you get longer rise times to peak. But a generic property, regardless of the black hole mass, is that as you go to as you leave the peak, the rate at which material falls back to pericenter goes as a t to the -5/3 power law. And you might also note that the peak accretion rate varies dramatically as a function of black hole mass relative to the Eddington rate for that black hole mass. So for the higher mass black holes, you're actually just sub-Eddington in your peak accretion rate, but for the lower mass black holes, you're highly super Eddington. So there's all sorts of interesting accretion physics to probe. And in fact, this simple picture is not exactly, there are some issues with this simple picture when we start looking in detail at the observations. So most of my talk, you should all be going like this. I'm not going to do the whole face. But most of my talk is going to be about surprises along the way. I think almost all of the observations are surprises along the way, and this is why the theorists have been very active in this field, and they still have a lot of work to do. But we're going to find, but we also have tons of work to do too, don't worry. So here is this tidal disruption event candidate, PS110JH, which is very notable because you have this nice cadence, nice sampling of the light curve. This is a logarithmic scale here. And in particular, you have the multi-band coverage, but in particular, you have this very nice sampling of the rise of the light curve. And this is a case in which we were observing, co-observing fields with pan-stars as well as with the space-based UV satellite Galax. And so we were able to catch its early UV emission on the rise, as well as its decline, before we had to figure out what it was. In addition, we followed up this event with HST, and while the optical emission is hard to detect in the nucleus of the galaxy, this is a very faint, this galaxy has no UV emission associated with its starlight, and so we clearly see this event still shining in the UV over 4 years later. And you can see, so the solid lines here are not a fancy radiative transfer model. This is simply taking these fallback curves, which know nothing about accretion physics, and basically placing them, scaling them up in the vertical direction onto our data. And so it's pretty remarkable that these light curves seem to be tracing the fallback rate so nicely. And we sort of confirmed that the UV is continuing to show this sort of characteristic t to the minus 5/3 decline. So you would think this would be good news, okay, because this is theory, these are observations. The problem is, it's not exactly that simple. While the bolometric luminosity in a tidal disruption event should follow a t to the minus 5/3 decay of the mass accretion rate, when you're looking in the optical band or the UV band, you need to think about band effects. So how is the spectral energy distribution of your emission changing with time, and how is that going to affect the band in which you're observing this emission? And so in fact, if you take the basic predictions of a disk model, and you say, well, the luminosity is declining as t to the minus 5/3, then you expect a t to the minus 5/12 decline in the temperature, if you're talking about thermal t to the 4th relation emission. And so in fact, in the optical bands, you're going to get increasingly more and more emission coming at the longer wavelengths as the emission gradually cools. And so instead of a t to the minus 5/3 power law in the optical bands, you expect a t to the minus 5/12 power law. So I would argue that the simplest way to get away with this is say, well, the temperature isn't cooling, or at least what Elizabeth called the color temperature is not changing. And we do see that. We don't see any evidence in this event or in other events, I think there's one exception, for any dramatic change in the color temperature or in the shape of the emission. So we need to understand that as we model these events. In addition, as James already touched upon, we also should be surprised that the radiation is coming out as efficiently as the fallback rate. And James talked about the issue of circularization, and I call this the great circularization debate of 2015. How many of you are aware of this debate? Many, right? It doesn't seem as impressive when I put am I missing some references? It seemed very impressive at the time. It was this flurry of theoretical work on just how efficient circularization is, and I think they came to a consensus that in some conditions, perhaps, and especially in the more massive black holes, we can get efficient circularization, and then, so we don't have to worry about this gap between the actual radiation coming out and the rate at which material is falling back to pericenter. So I think this may be okay, but this is pushing the theorists to think about the efficiency of circularization. Here's another summary plot of all the candidates, and here, I guess it looks a little bit confusing, but here I'm plotting the peak bolometric luminosity versus the color temperature. And I say here black body temperature because truly all of these events are well described by a black body thermal emission. So it's not simply just looking at the peak of the emission. But when you look at the luminosity and temperatures of these events, there seems to be a dichotomy in the color temperatures of these events, in the black body temperatures. So the candidates that have been detected by X-ray surveys appear to be hot, maybe I would say too hot, and the candidates detected by optical surveys appear to be too cool. And what I mean by too hot and too cool is that if you just think about what is the characteristic temperature of radiation coming from an optically thick accretion disk, that's forming at around the tidal disruption radius of the black hole, you expect emission that's peaking at around 0.02 keV, that's squarely in the EUV band, and I'm showing here sort of where you expect optically thick thermal radiation at about the tidal disruption radius. So it's sort of in this gap here. But this isn't too surprising because we're really limited in our observing capabilities. We're either looking in the X-rays or we're looking in the UV and optical. And so these X-ray candidates, it's not surprising that they have higher temperatures because they would not be able to detect any black body emission cooler than around 0.07 or so keV, because then if you had emission cooler, the Wien's tail would be in your X-ray band and then you're just out of luck. So this is not a surprise. But what's nice is in the optical and the UV, we are probing the Rayleigh-Jeans tail of this EUV emission, although we seem to be seeing, again, temperatures that are much cooler than you would expect. And that's also not surprising because if these events were much hotter, they would be quite dim in the optical. So again, we have a selection bias towards cooler events that are going to be brighter in the optical. And the issue here, which James didn't talk about much, is that these correspond to radii of about 100 times the tidal disruption radius. So this has invoked a whole new aspect to the structure in tidal disruption events where theory has needed to add an extended reprocessing layer to understand these cooler, bright optical transients that we think really are tidal disruption events. Note that a couple of these optical events and one of the GALEX events have been able to be discovered promptly enough that X-ray observations have detected an X-ray component, and shown here are the assassin X-ray counterparts, and here's the GALEX X-ray counterpart, and they are softer, and so that might be getting away from this selection bias. Okay, another really exciting surprise along the way. So the first time where we really detected clear transient broad lines, where we were to catch the spectrum of the event near peak and watch the broadline emission appear and fade, the first time we did this, it took us a while to actually classify the source because we'd never seen a spectrum like this before, and that's because it only showed broad helium line emission and no hydrogen lines. And I would argue that that is very, very hard to do when you're photoizing normal hydrogen-rich gas. Another set of candidates from the Palomar Transient Factory, one of them also showed this helium-rich spectrum where there are no hydrogen line emission, and there's another assassin candidate, 15OI, which also shows a helium-only spectrum. So there have been several explanations for this. And I, of course, prefer my explanation because, well, the reason I like it is because it's analogous to the supernova community in which where you see a helium-rich spectrum, it has something to do with the star. But I also like the tidally stripped red giant because it relates to the supermassive black hole. But there have been strong arguments against that, saying that's too rare. There have been some recent simulations arguing that you could, in fact, you could suppress hydrogen emission under certain photoionization conditions, particularly in the presence of an extended thick reprocessing envelope. But I would say we haven't really found a robust model yet. And that's because some events also show both hydrogen and helium lines. And so we need to be able to understand how we reproduce all of these spectral properties. But what's really exciting is that we're now getting detailed spectroscopic studies of these events, most in particularly the assassin events, and hidden in these line profiles are a dynamical imprint for the stellar debris, the structure and dynamics of the debris in these events. This is very exciting. And And we are already have another head scratching going on, which is this UV spectrum of Assassin 14Li, which was presented in Brad Senko's paper. And here again, we have completely a new surprise, which is that while we see broad hydrogen and helium features, and this is sort of a model prediction in red, we see these other emission line features, in particular very strong nitrogen features, but no low ionization lines. And so you can compare the UV spectrum of this source with quasar spectra. And while you can find a subclass of quasars known as nitrogen-rich quasars, which show some of these similar strengths in nitrogen features, they also show low ionization lines. So we're really seeing something interesting about the physical conditions in the tidal debris, and this is also very interesting. I'm not going to talk about the evidence for fast outflows in tidal disruption events, both relativistic and on-axis and non-relativistic and off-axis, so I'm going to let Ashley discuss that. But we also now have evidence for slow outflows. So we actually have high enough quality X-ray data and spectra which show not only this very nice thermal continuum in the X-ray emission of about 0.05 keV, but you also see these X-ray absorption lines which indicate an outflow of several hundred kilometers per second. So there are other ways in which we can catch tidal disruption events, and one of them is the expectation that if you have this flaring event going on in the nucleus of a galaxy, if it's in a gas-rich environment, you expect a sort of an echo of line emission as that flare photoionizes the local environment. And in fact, this was a potential explanation for a class of emission line galaxies known as extreme coronal line emitters, which demonstrate high ionization lines that fade over time. However, there was some ambiguity of whether or not these could be powered by extreme supernovae, in particular these type 2N interacting supernovae, which also can exhibit strong coronal line emission. But what's really fun is in this most famous case of an extreme coronal line emitter, we were able to recover the transient that actually powered the emission by looking at archival data from the linear survey, which is a white band optical survey. And you can see that it was discovered spectroscopically with Sloan and then followed up later, a few years later, with other spectrographs that showed this, these high ionization lines and they're fading with time. But with linear, we actually catch the transient that occurred over a year earlier, and we can actually constrain the rise, the start time of the event. And so you can look now at the you can subtract the baseline of the light curve and look purely at the transient portion of the light, and then you can compare it with some shapes of strong interacting supernovae, as well as this is PS110JH, the tidal disruption event from Pan-STARRS, or you could just fit it with a t to the minus 5/3 power law. And it's hard, the absolute magnitudes don't necessarily differentiate it from some of the most powerful interacting supernovae. The light curve, it could go either way. But I think the nail in the coffin on the supernova explanation is that this galaxy was also serendipitously observed by GALEX in 2006. And so we followed up this same galaxy with SWIFT in the near UV band, and we'd seen that the UV emission had faded dramatically. So that UV emission we were seeing here was in fact associated with the transient, and it's just too bright in the UV over a year later after the peak to be associated with a supernova. So I think, at least in this case, we can definitively say that this class of emission line galaxies can be powered by a tidal disruption event. There are other echoes that you can look for. Just a few days ago, Stuart posted this on the archive of the detection of a dust echo in a couple tidal disruption events detected in serendipitously in WISE, near-infrared observations. And shown here are the WISE raw photometry, where you can see this decline, and you see some models for the dust reprocessing. Please go see Stuart's poster, where he discusses his paper. And I wanted to show this sort of multi-band spectral energy distribution posted just yesterday by Jian et al. 2016, where they also claim to detect a dust echo. And I just wanted to say that here's an example of this very nearby tidal disruption event discovered by Assassin, as really has multi-wavelength coverage. And I would call this the Rosetta Stone, in that if we can understand this source across all of its wavelength range, maybe we can understand the the radiative properties of tidal disruption events and the accretion physics involved. So there have been other, I'll just conclude, I'm wrapping up, that there are interesting suggestions for a preference for post-starburst galaxies. We have this issue of too high and too low rates, meaning that if we assume the basic models for how tidal disruption events look, we actually shouldn't be finding them in optical surveys. But if we assume that they look the way they look, we should be finding many more. Do you understand what I said? Okay. So where do we go from here? We want more events. And in principle, we're going to have TDE factories. But I just want to say that with thousands of TDEs, we get millions of pesky supernovae, okay? And I'm sure many of you will agree that supernovae coincident with the nuclei of galaxies may appear as TDEs in your optical survey telescope. So we really need excellent efficiency to do this, and I guess I will conclude here, and we can talk about why we need the UV. Build a wide field UV satellite, as Elizabeth said, and I'll stop here.
I guess it was much more of a comment that I think there's a lot of parallels between the physics that's going on in the superluminous supernova we discussed and in TDs. There are obviously differences in their spectra, but fundamentally, if we believe that there's a central engine powering the superluminous supernova, it's sort of the same thing in a TD. We have some central source of X-rays or UV being reprocessed by some material, keeping a persistently blue color for the emission. So I'm just making a general comment that I think as theorists, and even as observers, we need to sort of, compare what's going on in these situations. I think there's a lot of parallels between the two types of events.
However, we've seen how thin these streams are. So the actual structure of the debris is so thin and confined to a plane, you still have to understand why you would get such extended thick structures.
Right. Understanding how we get the structure, but when I go through things like trying to figure out how we reprocess, what types of lines and spectra we get. Yeah, no, I agree. It's an issue how we get this wide reprocessing region.
Could you comment on the possibility of Assassin 15L being a tidal disruption event?
So I guess, has anyone gone to see if it's truly nuclear? Truly to what resolution? I mean. So, but it had a hydrogen-free spectrum, correct?
That's correct. So we will know the HST resolution if it's nuclear. So we will know if it's HST, to HST resolution if it's nuclear or not. Right now we have the first epoch on HST, but it's still bright. So how do you centroid to know where the nucleus actually is? We're based on ground-based observations right now, so that's quite uncertain.
Did you look, you looked in the UV?
You mean, so there's HST observations, I think it's B band, but I forget the exact band. Maybe someone else has also looked at the observations.
Because UV might be easier if it's.
But you also need a lot of stars. So because it's going to be systematic dominated, so you have to line up the two images. So if you go to the UV, you won't get enough stars to do a great job. So you have to go into longer wavelengths. But anyway, the point is that we will know once Assassin 15LH fades, we'll get another HST epoch. it's already been awarded, and then you can actually get to HST resolution to know if it's on center or not. But right now, that's not certain.
So I thought your event with the possible coronal lines was quite interesting. Is the rate that those are found in the survey consistent with the TDE rate? And do we expect to see these lines and TDEs we find optically or through the UV? Should we be looking for these?
Yes, so the time scales of the line emission are much longer because you're looking at gas at much longer light travel times. The issue, so most of the events that we've detected have been in gas-poor elliptical galaxies, early-type galaxies. However, maybe you don't need that much gas to be able to power the line emission. So it's definitely something to look for on longer time scales. That would be wonderful to see this line emission popping up. I don't think it's ever been detected yet for one of these candidates. We sort of did the reverse, where we saw the line emission, then went to look for the transient. But in the future, a spectroscopic follow-up should also be looking for that. But the rates, I'm not sure. I haven't looked at that.
Just on the question of the centrality of TDEs in their host galaxies, I wonder if we should be a little bit cautious in the sense that is it necessarily clear, first of all, that the photometric center is necessarily where the supermassive black hole is? And equally, is it necessarily clear that the supermassive black hole is always going to be in the nucleus of the galaxy, bearing in mind you may have an enhanced rate of TDEs in merging supermassive black hole systems, and so...
yes, so, and it also could be a recoiling supermassive black hole.
Exactly.
No one will believe you if you say that. Yes, I don't think we're getting to that accuracy where we're looking at really fine offsets. Not many of the events have been followed up with HST resolution. So I don't think there's been an event that had a very, very, subtle offset that then people discounted. But I think it's an interesting possibility. I mean, there have been prediction on the rates of these events around recoiling supermassive black holes where you might actually see a significant offset.
Just a general comment that there is another class of TDEs that would be very interesting to look for, and that's when you have a black hole binary, because in that case, the rate can be 1,000 times larger than in a typical galaxy, and that was predicted by many different people. Obviously, in the present-day universe, the mergers are not as frequent as they used to be at redshift 1 or 2. So if we extend our capabilities to go back in time and look for those merging galaxies, we might find a lot of TDEs that are in environments quite different from those that we find nowadays. And that could be a flag for those merging black holes.
Yes, although I think the duration of this burst and tidal disruption event rate it's finite, right? It's not very long-lived.
Well, it depends how long the binary survives, but
right.
It could be a giga-year.
Yeah.
If you
but yeah, there's so much really interesting information in the rates of events, even relating rates of events as a function of black hole mass to be able to address what James brought up about the efficiency of circularization. So if we're really finding a deficit of tidal disruption events observed around smaller mass black holes, that might be related to either circularization issues, but it also could be a consequence of the black hole mass function, or but you could also look for enhancements in the rate due to presence of binary. So yeah, so there's a lot of exciting things to be done with much larger samples.